Um, right. So basically, we're in the the part of the course where I think it's the most difficult part of this course, which is trying to figure out how to write a query. The syntax and stuff, I mean, like that's easy, but if you have a bunch of relations, how do you actually like write the query um, in, in the way that you'll get what you want back? Um, okay, so the way that we're doing that is by going over a few sort of representative examples, typical scenarios. And my hope is that by going over these examples, it covers enough to where um, if you're presented with a new query, you can figure out how to write it. Um, some of these queries are pretty straightforward. For example, finding restaurants frequented by at least a person under the age of 18. Um, uh, it requires a cross multiplication between um, the person's relation and the frequent's relation. So that builds one larger relation that has all possible combinations of people and places that are frequented. And then from that, you select only those rows where the names match. So that way you know that the this person is the same person who also frequents whatever restaurant, and their age has to be right. And the project is just because you don't care about any of the other stuff, you just want to know which restaurants there are. This is a join. Okay. This is another join where we're just showing that you can use different types of predicates for the select statement. Yeah, the select statement, we've now talked about what predicates are, and that's what the select statement is. Here we see a set intersection along with, I mean, it's really a join, two joins and an intersection together. This is just a straightforward join. And now this example is where we left off. Finding the names of people who frequent only restaurants serving at least one food that they like. And one way to accomplish it is with this query here. Let me erase these. Okay. With this query. And this query, I think, is a difficult one to arrive at. I gave it to you for sort of an unofficial homework to try to figure it out. And the last class, we went over this, and we'll pick this up again today. And I'm going to talk about how to do set division. We've talked about set multiplication. That is like a base operation, multiplication. Division is not. And we'll talk about how to do division today. But here, to me, it seems like it's a very mysterious thing, how to go from this type of statement to this type of query. So let me move this a bit. So the way that this query works is that you're returning the complement of something. So you say, in order to return the names of people who only frequent restaurants that serve things that they like to eat, I'm going to consider the people that I don't want, the people who are not those people, and remove them from everybody else. And then what will remain is the thing that I like. So I'll start with everything, and then I'll sort of carve out a region of people that aren't good, remove them, and then I'll have the result, the people that remain. Here, the people who aren't those that frequent only restaurants serving at least one food that they like, those are the same. There are people who either only frequent restaurants, or I'm sorry, they either frequent restaurants that don't serve anything that they like, or there's restaurants that serve things that they like, but they don't frequent them. And that is sort of the complement of people who only frequent restaurants serving at least one food that they eat. Yeah, let me go back to, well, let's say. Yeah, the reason why I think that this is hard is because it takes some thought. You know, I don't think that these types of queries, I mean, maybe if you do them long enough and it just sort of becomes second nature, but yeah, in the beginning, this type of thinking or this strategy is something that comes up many places. And here is one of them, which is, in order to answer the question, let's consider the complement. Let's consider it from the other side. And that is easier to do. So, is there anybody who knows the Monty Hall problem? Monty Hall. Yeah, Monty Hall. Monty Hall problem. Okay. Uh, uh, yeah, can you say what it is? Yeah, what's the Monty Hall problem?
Yeah, isn't that like the game show where there's like three doors and like I think for example there's like a llama in one of them and you have to figure out okay the host would say like okay here's one door that the object that you're trying to look for isn't there and now you're left with two more doors. So some people would say like you have a 50-50 shot of getting it right, but actually I think it's you have a higher percentage of switching doors and saying that the object that you're looking for is not the one that you previously thought of.
That's right. Okay, good. Yeah, yeah. So this is yeah, very good. Thank you. Um, let me turn this off real quick. So the Monty Hall problem. I mean, you should learn this in any statistics class or probability class as well. Um, so the Monty Hall problem. This is named for a game show where there were three doors, and behind one of the doors, there's, I don't know, $1 million. And so a person is there with Monty Hall, and the person picks a door, whatever. At this point, I don't know, they pick door number one. So they have a 1/3 chance of being correct. The other two doors, who knows? But yeah, so they have a 1/3 chance of being correct. Now Monty Hall opens a door. I'm not an artist. He opens a door and shows that there's no money behind that door. And now Monty Hall gives the person the option to change his mind. Does he want to stick with door number one, or does he want to switch to door number two? And most people think that this it doesn't matter what he does, because it's a 50-50 chance. I mean, now there's two doors, and but in actuality, he should change his mind, and he has a 2/3 probability of being correct if he changes his mind. This is a surprising to a lot of people. I'm not going to work through it, but it's a very interesting problem. And one thing that I think helps make it click with people that changing your mind is a good idea is not to consider in the beginning what was the probability of the person being correct. They had a 1/3 probability of being correct. But to consider instead what's the probability of them being incorrect. So if they had a 1/3 chance of being right, that means that they had a 2/3 chance of being wrong. So their first choice, whatever it was probably wrong. And now a door is opened, and you didn't pick that one, but your initial pick, you had a 2/3 chance of being wrong. So now, if you change your mind, then you will have a 2/3 chance of being correct, right? You've corrected your error. Or, if you were probably wrong now, and now you have a chance to switch to the only other option left, well, then you'll probably be right to do so. So anyway, this type of considering complements, and considering the complement of something is often easier than considering the original thing. So in convex optimization, for example, this is formalized. There's the primal version of a problem and then the dual version of the problem. They're both equivalent, just in two different settings. And each primal problem has its own dual problem. Each dual problem has its own whatever. So this is an example of a query that encourages you to do this, to consider the complement of the people who you're looking for. In order to find the people who you're looking for, instead collect together all the people that aren't those, get them out, and then you have what's left. So yeah, there's a process that I think you can go through to have a procedure in order to land on a proper query. This is sort of off the books, I mean, like all this quantitative reasoning stuff are things that it just help me make sense of what these are. Okay. Okay. Well, let me pause. Are there any questions so far? I hate talking too long and not checking in with students. No. Okay. Then uh, the quote unquote procedure. Um, so first of all, here, this whole thing of taking people, carving out people who you don't want and removing them, you know that that's going to be a set difference. And um, uh, within that set, you want it to be everything that the original thing wasn't. So you have a set difference because you're going to be removing the things that you don't like, and then defining the things that you want to remove. It's just not the other thing. So these are the two knots. The first knot is going to be a set difference. The inner knot is going to be all of the things that you don't like because you want it all in one package and you're going to be removing it. So it can be worthwhile to try to formalize or to state in a kind of lower level language what exactly it is that you want. And so if you want the people who frequent only restaurants that serve something that they like, you can state it sort of more formally as you want people P such that for all restaurants that this person frequents, there's a food that they like to eat there, and well, that's it. Actually, there's a food that they like to eat, and the place serves the food. Okay, so for all of the restaurants that they go to, the restaurant serves something that they like. So in order to remove the people that don't fit that description, you can take a knot and then just distribute it across the entire predicate. So for all gets switched to there exists. Oh, I don't know why these are all off. Oh, I see. Because I see. There you go. Oh. There. Okay. So the first for not so for all restaurants that this person goes, there's a food that they like to eat, and the restaurant serves it. So the opposite of that are when there exists a restaurant that the person goes to, where for all of the foods that they like to eat, for all of the foods that the restaurant serves, yeah, the person doesn't like to eat it, or the restaurant doesn't have it. So the first knot, or the knot flips the for all to a there exists. And, oh, by the way, there was a good question last time. Why doesn't this part in gray, for all restaurants X this person goes, when you apply a knot to it, why doesn't that become there exists a restaurant that this person doesn't go? Instead of there exists a restaurant that this person does go. So, yeah, that's the reason is because you're taking a statement, a presumably true statement, and saying that if this statement were false, then this other thing must be true. Okay, that's what the complement is. So you have two statements, one of which must be true. Either it's true for all things, or there exists a case where it's not true, in which case the there exists statement would be true. So, and if there doesn't exist this thing, then that is to say that for all things, it doesn't exist. So, um, uh, so the statement that for all the restaurants that this person goes to, if you're negating that and you're saying that it's not true for all restaurants that they go to, then it must be the case that there exists a restaurant that they go to where the thing is not true. Hopefully that makes sense. Yeah, I mean, it would sort of be a non sequitur, I guess. For all restaurants this person goes, something something, and then if somebody else said that's not true because for all the restaurants that they don't go to, like that's another topic. We're talking about restaurants that they do go to. You're trying to say something that's true for all of them. If that's not true, then it means that inside, the set, that there has to exist something that makes it not true for all of them, because it's not true for this one. There exists one. Okay. So that is to say, if this statement is wrong, if it's not true, then it must be true that there exists a restaurant that this person goes to where for all of the foods that they eat, the restaurant doesn't serve it, or otherwise for all foods that the restaurant serves, the person doesn't like it. Okay. Yeah, and then the other not is the set difference. So this sort of highlighted in red thing, that's the complement of the set. That's everybody who's not who you're talking about. And it's easier here. In fact, not easier. It has to be phrased in this way for SQL because of the way the select operation works. At the end of the day, it comes down to the select, and the select has no memory. The select, it looks at the data like this, just like it can see one thing at a time, one row at a time, make a decision and move on, and it can never revisit that decision. And so it only really works for the existence of something. And so, yeah, there's, yeah, I believe that there's a relationship between predicates and the SQL language. Okay. Are there any questions about this? Because this is one of the harder queries. You don't have to go through this process, by the way. I mean, this was my own. Can I re-explain the not? Yeah. So we are going to be rephrasing the query. Okay, so the way that it's phrased, it's like there's something kind of wrong with it. But you can say the same thing a different way, and it's not only the same thing, but this different way is easier. It's easier for the system, anyway. So how do you rephrase something that's true? I mean, there can be a statement that's true. One way to rephrase it, one way that you can always come up with an equivalent statement will be if you apply the not operation to it 2 times. If it's, oh, sorry. Oh, whatever. Okay, sorry. Somebody just called in. I muted you. If you had a question, you can unmute. Sorry. Okay. Right. So the not, it's an operation that is, on its face, it's pointless because it's the same thing. If something is not some way, then you've done nothing to it. It's like adding 0 or multiplying by 1. But so that on the one hand, it's not changing anything about the true statement. On the other hand, each of these different nots are going to have a different type of effect on the statement. The result of which will be an equivalent statement, but it'll be phrased differently. So instead of this statement, find the names of all people who frequent restaurants serving at least one food that they eat. Really, this is going to end up, find the names of all people who aren't those who frequent restaurants that serve only things they don't like or otherwise serve nothing they do like. Okay, so these are the same. They're saying the same thing. It's just that this way, if you phrased it this way, it would be more straightforward. But how, yeah. So this this outer not is going to be a set difference. So that's saying, okay, instead of returning these people, we're going to start off with everybody, and then we're going to remove people. So that's the first not. That's going to be a set difference. And then the inner not finds the complement of what you want to remove. So exactly those people that you don't want is what the inner not does. And because you have 2 nots, then you know that you haven't changed anything about the set that you're returning, about something being true for each member of that set. Okay, good. Any other questions? Okay, so yeah, really this is just kind of a strategy that is common many places, like, in my opinion, understanding the Monty Hall problem, in convex optimization, whatever. It's a strategy of considering the complement. And this is an example of that. That's really what's happening here. That's why the query looks this way. Because it sort of has to, I guess. I don't know. Like, yeah, the yeah, the relational algebra kind of only understands the complement, so that's why you have to put it in that form. Okay. Um, okay. So I want to talk about set division. So let me do that. Okay. So here, okay, let me turn this off. All right. First, I need to define what set division is. So we've talked about sets and set operations. So we know that sets like relational algebra, these are also sets. They're operations. You can add sets together. This is like addition, the union. You can intersect sets, which is something that an operation that is a new operation for sets. You can't really intersect numbers. There's the subtraction, the set difference. There's multiplication, but set multiplication. This is all possible pairings. But we haven't talked about division. And now these are basic operations. Okay. The division is not a basic operation. Instead, you have to use a combination of other operations in order to achieve it. So what does it look like? If we have a table T1 and a table T2, actually I'll make that a small table. And let's say this has columns A and B. And and this has a B with just P2. Okay, so T1 divided by T2 is going to be this table. Okay, so So this returns all entries A such that T1 has an A-B connection for all B's in T2. So, okay, division is AB divided by B is equal to A. This is sort of what we're trying to reproduce, this effect. Okay? If you have something AB and you divide it by B, then you'll get A back. So what this does is it finds, here's P2, and P2 appears 4 places. These 4 places. And we want the values of A that correspond to those. And this is another big part of it. This has to be true for all of the B's in T2. This is the simplest case when T2 only has one entry. If we had, I don't know, P1 here, then P2 has these connections. P1 has these two. And therefore, the only values of A that have a relationship with all of these is the number 1, because there's P1 and P2, and the number 2, because it is also connected with both P1 and P2 somewhere. So the result of this would be 1 and 2. Questions about division, or what it means to do set division? I mean, if I gave you 2 tables, would you be able to do this?
So, Professor, there is no repetition in the final result, right?
There is no repetition.
There's no repetition, okay.
That's right. Relations work like sets, where you always write a set using as few elements as necessary. For example, these 2 sets are the same because it's just whatever. I mean, just by definition, they're the same. So you can always prefer to get rid of any repeats because
Thank you.
they're no different. And in the same way, relations are sets, and so yeah. This will also be enforced because I mean, we're not making it explicit, but this relation will have a primary key, and primary keys are unique for this reason. They're unique because they're like members of a set. No repeats, not allowed. So, yeah. Okay. So I need to pick on this. How about Mark? You have a mic?
Hello.
Hey. I just want to go through like a couple, I don't know, examples of division, just to make sure that people understand how it works. Okay. How about if I just have this P2? What is the result?
So if you said P2 for so the division would only put out 1, 2, 3, 4, correct?
1, 2, 3, 4. Yes. Okay. Good. Yeah. Sorry. Let me just write that down for a good measure. It would be 1, 2, 3, 4. Okay. How about if we did P1?
1, 2. Would it just be 1 and 2?
Yep. Okay. 1 and 2. Perfect. What if it's P1, P4?
And that's where my question is. So the output has to be the values of A where it has both PR. Okay, so P1, P4. So would it be let's see, 1, 4, 2. Would it be nothing?
It's not nothing.
Not nothing. Okay, I can't see. P1, P4. Oh, sorry. 1.
1. Yeah.
Yes, I'm sorry about that.
Oh, yeah, no problem. Yeah, yeah, great. Yeah, because 1 has P1 here and P4 here. Yep, great. Okay. You feel comfortable with that division?
Oh yeah, yeah, sounds
Okay,
good.
wonderful. Great. All right. Um, okay, so uh, now how to achieve this? Okay, like you can do it hopefully now in your head. Like if you see these tables, you can go through it. Here is how this breaks down. So we only want, you know what, actually, okay, yeah, we'll see. Uh, so if you understand the division, like the way that the operation should work, I want to give you, I don't know, 10 minutes to try to figure out what this query would look like. Here. Yeah, if you can do it in your head and you understand it, then yeah, I want to give you an opportunity to try it for yourself. So please do use the 10 minutes to actually try to figure out how you might achieve this. Yeah, after that, I'll come back and see what you've come up with. All right, see you in 10 minutes.
Hi, Professor. Can you hear me?
Yeah. Um, yeah. Were you able to come up with anything?
I honestly wasn't too sure how you would go about doing this. Um, but I think maybe starting by like cross multiplying T1 and T2,
Mm-hmm.
and then seeing like selecting the and doing a rename so like B is B2, and then selecting where B is equal to B2. But I got stuck in trying to figure out how to get the ones where only getting one of them, you know?
Okay. Um,
I think you could maybe use a set difference, but I wasn't sure like what the constraints would be.
mm-hmm. Okay. Sure. Yeah. Uh, so this is part of it. There is a cross multiplication. There are set differences. Um, yeah, this is another case where thinking about the complement is um, is the way to go. Um, okay, good. Well, let me go through it. Unless anybody else would like to share. Maybe what they were trying or where they got stuck or something. There it is. Um, okay, so why this? Um, so again, it's a set difference. We use a set difference here. Uh, I don't know. I should try to come up with a quantitative statement with how that would work. Um, well, let's just go through it sort of bit by bit. Here, this part. Um, this is finding all possible AB pairs. So this is taking just the columns of A. So projecting it will, just leave you with those individual A's. And you cross multiply it with T2, which means that, you'll have that pairing, you'll have this pairing, you'll have that pairing, and you'll have that pairing. So those are all of the pairings that could possibly exist. And from that, you remove the real AB pairings. Remove actual AB pairs. And so what you're left with, this, these are all AB pairs that potentially could exist, but don't. And now, from the actual table T1, so just those A's, you remove any entry that has a potential connection, but doesn't, because it should. All of them should, you know. Okay. So, so the way that you find the B's, I'm sorry, those values of A that do have a connection with every value of B in T2, then those are the only ones that would remain if you remove any entry that's missing a connection it should have. So if you take out all the ones that have, you know, when we apply this here, I don't know if I should go through. I can go through like this concretely if there's any student that would like to see it. But yeah, this is sort of also a complement idea. So take table T1. Can I do it concretely? Yes, please. Okay, let's do that. Let me copy previous one. Sure, very good template. No, I'm with 2. Not that it matters that much, but whatever. Okay. So here's our table T1. It has some column A, some column B. What is it? 1, T1, 2, T2. Oh, no. 1, T2, 1, T3, 1, P4, 2, P1, 2, P2, 3, P2, 4, P2, 4, P4. And this has what? P1 and P2. Oh, why that's so small? Whatever. Okay. So the goal is to find all of the entries in table T1 where for every entry in, I'm sorry, T2, there exists a value of A connected with that value of B. And it has to be for all of the values of B. such connections exist. Here, the result, again, is just going to be 1, because only one, here's a connection with P1, and here's a connection with P, oh, sorry, no, here, there's a connection here, 2 also has a connection, and that's it. So then the result would be the number 1 and the number 2. So, okay, fine, that's the result. A, 1, 2. Okay, so that's the result. How does the above query get us this result? Okay, so first we consider all of the, let's just come up with all of the possible pairings first. So we want ones where there's where the pairing actually exists in table T1, but right now we'll just imagine what's everything that could be. So T1 cross T2, sorry, not just cross T2, this is the projected T1, because this is the what could possibly exist. So T1, project A, do this. Room. Okay, so we take table. What is going on? Weird. So we only want pi A of T1, which is just the numbers 1, 2, 3, 4. Again, no repeats. So we only need 1, 1. We only need 1, 2. We only need 1, 3. And we only need 1, 4. Great. Then we cross this with T2. What does it do? Okay. So 1 can be paired with P1, P2. 2 can be paired with P1, P2. 3 could be paired with P1 or P2. And 4 could be paired with either P1 or P2. Right, so these are all of the possible pairs that, that could exist. And now from these, we remove the ones that do exist. So here, this one, that exists here, so we remove it. This, that exists here, so we take that out. 2P1, that exists here, so we take that out. 2P2, that exists here, so we take that out. 3P1, not in our list, so that is a potential one that could exist, but it doesn't. So we keep it. 3P2, that exists, so we take that out. And for P1, we keep, because that could exist, but it doesn't. And for P2, we get rid of. And so this is this table, okay? So this table now, with these two columns, 3P1 and 4P1, these are connections that could possibly exist, between elements in values in column A and values of column B, but they're not there in the actual table. And therefore, the number 3 is missing a connection it should have. We want the ones that have all possible pairings. So, for example, 1 doesn't exist on this list because it actually had the 2 pairings it was supposed to. 2 also has all of the pairings that it's supposed to. 3 has 1 pairing it's supposed to, that one it's supposed to have, but it's missing this. Oh, let me use a different color. 3 is missing this connection. So 3 shouldn't count. It's missing something. 4, likewise, is missing the same thing to P1. It does have the connection to P2, so that part's good. But it's now missing a connection. Therefore, this table here, that's the table of losers. That's the table of people who are missing something. And we don't want the losers, so get them out. And therefore, 3, you're a loser, you're out. 4, you're a loser, you're out. And you return the projection of A. And again, because no repeats, you'll get that result. That's it. Does that make it clearer? Is it? Are there still questions about this?
I mean, now that I see it, I understand it, but I could never come up with that. But I see it. I mean, when you did it, I see it.
Yeah.
But I would never be able to come up with that.
Yeah. I think that's the real hurdle. That's why I think that this is the hardest part of the class. Because, again, you can understand it, but how on earth would you come up with it by yourself? I think there's 2 parts of it. One is, obviously practice, seeing more examples and stuff like that. Also some people, they won't know how to write a query, ask other people, somebody will come up with it. Oh, thanks. And, people, or I don't know, oh, I saw a really interesting query. Look at that, whatever. So there is a process of learning. Then there's also some strategies. And I think that one of the strategies is what I was trying to make the focus of today, which is considering the complement. Finding the things that have something wrong with them is easier sometimes. And so you find the things that are wrong and you get rid of them.
So I feel like if we do more like problems of this sort, it would become easier. Could you refer us to what part of the textbook? Does the textbook have more examples that we could walk through and try to do it ourselves?
Not really.
It
No.
doesn't.
No.
Okay.
Yeah, it has like this basically. Hey, how's set division work? There's the query. Yeah. The next class I'll pick up with another example of this. In fact, here I'll just give the query now for if you want extra practice. This is
Sure.
set division as well. Let me. Oh God, out of page. Okay. Find the names of all people who frequent all the restaurants serving at least one food they like. Okay, so This is slightly different than the query in example 5. By the way, class is over now. You can log off if you like. But yeah, this is an example. So same 4 tables. People frequents, eats restaurants, and it's different than the last one. In example 5, that's people who only go to restaurants that serve at least one thing that they like. So you will never find them frequenting a restaurant with something where everything on the menu they don't like. This is a different group of people where if they like something, they have to have it at every single restaurant that serves it. Like they really like pizza, and so they want to go to all of the places that serve pizza. And yeah, okay, so that's it. This is another example. You can work through it. I'll go through this on Friday.
Thank you, Professor.
Sure.